The magic formula has arrived. You should have hopefully watched the introduction video on what the heck does the magic formula do, so you have a big picture idea of the magic or the marvels that this thing can do for us. Basically, it's going to give us a curvy approximation to a curvy function, which is better than a linear approximation to a curvy function. You want to install this into the memory banks of your brain because we're going to need to use it, and stick with this entire video because the AP test writers are going to find clever ways to see how comfortable you are with this procedure. Many comfortable ways. I've written this formula in two different manners. They look all pretty much the same, but every once in a while a different publisher will use a different set of symbolism. So the only difference you'll see between these two is I'm using an A to represent the x-coordinate of attachment, and here I'm using a C to represent the x-coordinate of attachment. And you can think of that attachment x-coordinate as the same thing as the x-coordinate that you would attach a tangent line to a function. So thus it's kind of called the center very frequently. The example we used in the opening video was the friendly function e to the x, and if we were to attach a tangent line at x equals 0, the point of attachment, we would get this. You know to build your point and your slope and then use y equals mx, well, y minus y equals mx minus x. The Taylor polynomial using the magic formula, and I don't have the work shown here, will give us this. This is also centered or attached at x equals 0. Just a heads up for your future, it's a little bit confusing. This represents the x-coordinate at which we've attached, but this represents an x-coordinate that you are allowed to plug into the formula once you've built your equation. So they're both representing x's, just in a different purpose or a different manner. And finally, before we get going on the mechanics of this, you might say, what is this? This is new symbolism that you might not be used to, but it's going to be really easy. It's just a way to denote what derivative you're on. So if I have the function 2x to the fifth, its first derivative is 10x to the fourth, and you can see I went second, third, fourth derivatives. Well, if you want to write that in a different way, you can put a little inside a parentheses number, and that will tell you what derivative you're on. So f, and then kind of like an exponent, but it's not an exponent, in parentheses 4 of x, that's 240x, which is the fourth derivative of your function. And by the way, a little nuance to this, the original function is a function in which you haven't taken a derivative yet, so we would call that the 0th derivative. Here's my first derivative, here's my 0th derivative. So that gives you a little bit of an idea of what's going on inside this formula, but you won't have a real appreciation for it until we go through a problem. So we're going to go through a problem. We're going to build our very own Taylor polynomial, and it's basically, this is the fancy word for saying a curvy approximation of a curvy function. The function we're going to use is 1 over x, and we're going to attach our Taylor polynomial at x equals 3. So by the time we're done, we'll have a multi-term polynomial here that will be a darn good substitute or approximation for that one. And along the way, we're going to be using this formula. In the beginning, especially this first example, I'm going to be ultra organized. And being really organized is going to be helpful. When it comes down to it and you're a veteran of this, you're probably going to shortcut some of this organization for the sake of time. But I'm going to look at this formula, and basically every moving part in that formula, I'm going to try to get its values into the nice organized chart. So, for example, we're going to go from n equals 0 to infinity. We won't go to infinity, but I'm going to make a list of my n values. So here I go from n equals 0, 1, 2, 3. That's going to take care of this. Now if I look at this part, this is symbolism that's saying the nth derivative at a value a, and a is where we're going to attach this. Well, we're going to attach it at x equals 3. So I'm going to need two things in my chart. I'm going to need the series of derivatives, and then I'm going to need what happens when I evaluate them at the center, which is in this case a. So I know the star of my show is 1 over x. So now I do a series of derivatives. Its zeroth derivative is the original function, and I turned it into this because that's going to be easier for derivatives. And then I went through and in this case, we're only going to the third n, so I went to the third derivative. If I want to attach symbolism to this, this is f third derivative of x. So that's starting to address this situation, but this says I need my nth derivative evaluated at the center where we're attaching. So in this case, it's at 3. So I'm going to go ahead and plug a 3 into every single one of these. What I'm doing is I'm taking the important parts of this and putting them in an organized chart. This looks like an important part, n factorial. So here's my n's. If I turn those into factorials, I now have it available for me. My job now is to take all of this information and write out a series of terms. If I take this information following this guidance, I'm going to get the series of terms that is the Taylor polynomial. It looks like I've ignored this part in the chart, but don't worry, you'll see why that's not a big deal. So now we'll start taking this stuff and putting it into there. And I'm going to be very organized about this part too. So I make a little compartment for n equals 0, n equals 1, n equals 2, n equals 3. And in theory, I'm going to go out to infinity. I'm going from n equals 0 to infinity. Now for my n equals 0, I say, what is my f0 of a? Well, if I've done my chart very clearly, here's n equals 0, here's f0 of a, the derivative evaluated at a, in this case x equals 3. So the f0th of a is 1/3. That goes there, which is that. N factorial in the denominator, well, 0 factorial is 1. That's kind of a weird thing. But I'm going to write 0 factorial, and eventually I'll turn that into a 1. And then the other piece doesn't come from here because it's this easy. I just literally write x, that stays always, minus 3 to the 0 power. X minus 3 to the 0 power. So I'm going to do that for every n. You don't need me to explain my way through it, but I'm just going to go over to n equals 2 to show you one more example. By the time I get to this one, it says, what is the second derivative evaluated at a? So in my chart, n equals 2. Here's my second derivative. Here it is evaluated at a. That's how that gets there. X minus a, in this case x minus 3 to the n. N factorial, which is 2 factorial. And that is the third term in the series. Now I could keep doing this all the way. This is going to look a bit like a mess, and sometimes on an AP situation you might keep it looking like a mess because you're allowed to do that. But for right now, we're going to go ahead and start making it a little bit more approachable. And so when I do that, it becomes something that looks very reasonable for us to work with. This whole thing, when I do some reducing, is just 1/3. I do the reducing for every single parts of these. I get that thing, and what I end up with is this polynomial. Now the symbolism says this is a polynomial third degree approximation. And this 3 tells me it's third degree, meaning I went out to the third exponent, or exponent of 3, I should say. This doesn't mean 3 terms. In this case, we have 4 terms. Sometimes some of your terms can be missing, and we could have 2 terms that are a third degree polynomial. But this is your third degree Taylor polynomial approximation of 1 over x. The word approximation is important because, as you remember from looking at the video, this isn't going to give you the exact substitute of 1 over x, but it's going to give you something darn close. So that's why we call it an approximation. Believe it or not, if we were willing to go beyond 3 and go out to infinity, that's going to be a lot of work if we go out to infinity. But if we're willing to do that, this would literally be the same as 1 over x. Crazy talk, huh? So I'm going to summarize here for a second. Here's the function we're working with. If we went old-fashioned AB style and built the tangent line, it would look like that. If we went New Age and did the BC Taylor polynomial approximation, it would look like that. And check this out just for giggles. If I take my function and I plug in a 3, its value is 1/3. And the linear approximation and the polynomial approximation all should give you 1/3 if you plug in a 3, because that's the center of attachment. At the center of attachment, the curvy function and the linear function and the curvy approximation, they should all have the same x and y values. But as soon as we move away from x equals 3, then we should start getting a little estimation error. So if I move away from x equals 3, the real value of the function is 0.3125. If I'm using the linear approximation, I get 0.3111. That's pretty good, but as you would guess, because we moved away from the center of attachment, we start to get a little bit of an error. Well, with this curvy approximation, look how much closer it is to the real deal than the linear approximation. That might not seem like a big deal, but I think the math people would say that's a big deal. And this almost identical value is just going out to the 3rd degree. Imagine if we wanted to be more precise, or if we wanted to move further away from the center of attachment and still be precise, we would just need to go to a higher degree. And we could do that if we wanted to. We just need the time. A quick break for some vocabulary. I've been using the word Taylor polynomial to say what we're doing, or Taylor polynomial approximation. There's some vocabulary here. A Taylor polynomial can be the polynomial approximation where the center or the point of attachment can be any x value at all. In the example we just did, I believe it was at x equals 3. A Maclaurin polynomial is just a special version of the Taylor polynomial, and it just is centered at x equals 0. So if you ever run across a problem and it says we're working with a Maclaurin polynomial, that's just a fancy way to say we're going to center this at x equals 0. As an example, you'd be able to spot it very easily. Here's the Taylor polynomial approximation that we just did, and it's centered at x equals 3. You can tell that by looking at this, and what you're really referring to is this part of the magic formula, which says x minus center, x minus center. A Maclaurin polynomial might look like this, and keep in mind I just made this up. I didn't go ahead and calculate it. But if for some reason we got a Taylor approximation, we got a polynomial approximation and it looked like this, I would know right off the bat that this is a Maclaurin polynomial, because x cubed is like x minus 0 cubed, and 0 is the center of attachment, thus making it a Maclaurin polynomial. So that's your first run through. It's definitely a tedious process. There is a lot of neato math going on. I highly, highly encourage you to make good friends with this process, because the AP test writers are going to take this mechanical process and turn it into their playground of deep, mind-bending questions. The more comfortable you are with the process, the more you're going to be able to roll with it, and it's going to take some decent rolling. So practice, be very, very organized, take more space than you think you need in the beginning, and once you become familiar with it, you'll be able to shortcut the paperwork and the time work. Enjoy. This is the magic formula.